Okay, so I'm going to start this one off by showing you what I'm about to do. So this here is a Maxwell construction on a pressure volume, specific volume diagram. And what this is this is an isotherm, and these are these three intersections here. That's what we calculated in the last video. Those three roots for the specific volume of some pressure involved for some pressure and temperature using the isotherms. And what we're now going to want to do is we're going to be calculating the areas underneath these curves, because these curves don't exist. Based in, like, here this would be like a water vapor equilibrium, I believe, and then this would be a vapor gas equilibrium. Something I'll correct myself later if I'm wrong on that. But so that's what a Maxwell construction is. And don't worry about the stuff underneath it. I'm about to use that. That's from some Wolfram Alpha stuff. And so now, let me go back to what we're going to do. There's two ways to do it. So one, we're going to do it using a quad function. So we're going to do area quad, or just area Q. And that's going to be with respect to pressure and temperature. And so once we do that, we're going to want to define an integrand, and we want that to return our pressure minus our cubic pressure that we had earlier. Cubic P, and that was with respect to V and T. We're going to use our roots, so just V1, V2, and V3 are equal to the cubic V, and that is, again, with respect, it's right here, with respect to pressure and temperature. And then we want to return our quad with the first integral, which is V1 to V2, and that is V1 minus, no, V2 minus V1, because those are the limits of integration. Or does it just V2 comma V1? Let's try V2 comma V1 first. And then quad, and then this is V2 and V3. Go ahead and run that, and then test it out using the values 9,100 Pascal, 91,000 pascals, and 373.15, and shift enter. Okay, so let's try the minus then, because that's probably what it is. Okay, so it is commas. You just do this, not what I was doing. Because you have to give a function, then the limits of integration, not the function of the limits of integration. That's not how this works. Okay, so those are the correct values, so it means I did that right. And then there is another method, which is actually called, which is just integrating, so area I, and that's P and T. And this time we need the help of A, B, epsilon, and sigma again. And those are going to be equal to cubic abs. And that is, I believe, with respect to temperature. And so we're also going to want to define an integral. So this is just going to be integral. So integ, and we want the integral to be of this thing that I wrote down on the board, which is, well, let me shed some light on the subject here, that I wrote down on the board, and we have, this is a long one, A times log no, numpy log 10 of b times v minus, no, plus b times sigma plus volume minus a times numpy log 10 of b times epsilon plus v plus b times p times epsilon minus sigma times v over b times epsilon minus sigma minus r times t times numpy log 10 of the absolute value of b minus v. Okay, I might have gotten some of this, so actually I think this is going to be this, yes. So I delete one here, because I didn't highlight how I liked it. Okay, so does not, okay, so it is, so it's this big long thing. Oh, no, don't want that there. Integrate's not the one that I'm going to be using anyway, since I already have the quad working. I guess I can come back to it, but it just does not want to work. So, okay, so the next thing we're going to want is to find the difference of these areas. So we're going to define a function first. Define the difference. And this is going to be with respect to some vector and t. So because we need just a vector and temperature. And then we want, and then pressure is going to be equal to this vector. And since this vector is going to return an array, we want just that first value of the array. And so we're going to have our first area and our second area are going to be equal to the quad area of t and p. No, of p and t. And then we're going to want this to, why do you still say it's not defined? It's defined right above you. You'll be fine. Return a1 plus a2, considering a1 is going to be negative. And then run this. And then to test, we need to solve it with root. And to solve that, we want the difference function. We want the starting pressure to be 10,000 pascals. And then we want the temperature to be equal to 373.15. And this should give us, well, it's not, that's not going to be right. Still not right. Function size between calls. I gave you a function, I gave you that, and I gave you the arguments. What do you want? Okay, I think I know what I did wrong. So it's saying the array size is not the same. So I just need, and that's because this returned like this array here, right? So no, what I need is this to be the first term, and this also to be just the first term. So let's try this and see how it likes that. See there, that's a little better. Oh, well, that's not going to run anyways. Still, what is it? Can I unpack uniterable float? Okay, let me try something else. Let me try switching the order here, see if that's the difference. Still going to be the same thing there. Oh, okay, so it was the difference, and so this does work. Okay, okay, progress. Now it's time to move to the next part. Okay, so the next thing to do is we're going to plot that bell curve that you see in most preview diagrams. It's something along the lines of this, or it's going to look something like a parabola. So we've already plotted one point of that using this right here. This is just one point. So what we need to do is make a bunch of other points, like plot the rest of it. And to do that, we need to start by making some lists. So we're going to need the vapor pressure list. So PV is equal to, PV list is equal to that. And then we're going to need a volume of the liquid list. And then we're going to need the volume of gas as a list. And it's going to equal that. And then we're going to need a bunch of guesses, and our starting guess will be, let's say, 100. And we're going to make that a float. And to start this, we're going to need to go and make a for loop for x in range numpy linspace, and I always forget this because that's important. So there's that. So first we're going to make the vapor pressure this value right here. I've already copied it. So nope, equals this, but we only want this value right here. So we need to make this dot x to get just that value, and to make it the first one of any list, we need to make it 0. And then also we need a t, and I have it right down here. T is equal, let's just use capital T. T is equal to the critical temperature. Temperature minus 275, and then times 1 minus the e to the negative x minus, plus 275. And then we're going to want to make our, and then we want our guess to become the vapor pressure for each one of these. I don't know why I keep pressing enter so many times and then just forgetting that doesn't work. And then we want to get the values for these two. So we have our liquid volume, some intermediate, and then the vapor or the volume of gas. And that's going to be equal to cubic roots of, and that's going to be equal to the cubic V function that we made earlier. Not plus V, cubic V, but instead we want the vapor pressure and temperature. And then so run that. Okay, already got an error. Integer and scalar, so no range, maybe? Because that's what range does. So then we have our liquid volume list, VLL, append, all new values of vapor of this, so VL, and then we want to VGL is equal to, VGL dot append VG PV append our PV. And I run this, and I still run into a problem. There's no attribute to append. Oh, PBL. What do you mean cannot unpack? Oh, did I not? I changed that to guess. Oh, I didn't when I last did it, so. Still don't like it. Or do you just want generic arguments as generic T? Okay, that would make sense if it was generic T. Now it's this. Oh, duh. Temperature in front. Hey! And in order to plot the stuff, I also deleted the integral method, or the integration method. I just do not have the time for that. So, sorry. If you wanted to see that, you can ask me and see it. I suppose also I'm going to need a plot for this. So, our p plot, or just pp, because I'm lazy, is equal to our pvl list, and that's gonna be colon, comma, colon, semicolon, no, colon, comma, ooh, I always forget how to do this. Okay, so it's just gonna be this list plus the list again, and this time with the colon, colon, and then we want vplot, or just vp, to be our vl plus vg, and and plus the same thing it was last time, the colon, colon, -1. Huh. Invalid syntax to scalar variable. Oh. It's the lists versions. It's not going to be just the regular variables. I gotta remember what I did. Yikes. Okay, it likes that better. And in order to plot this, just gonna, I've already copied that. And this, you'll notice, I just increased the range on here because it was only showing it to I believe, a certain point. So I want to show all of that. And then I want another add scatter. No, I just need one figure. Add scatter, and then I want x is equal to our v plot that we just made. Y is going to be equal to our p plot, pressure plot. We want the mode is lines, and we want to make the marker color something we can see, so green. You'd better like green. Yep, there we go. And so we have our pressure volume. I guess this is from the Maxwell construction. And so we have the two phases. They meet up together like in the middle somewhere around here. But this is our two-phase plot for the Maxwell construction.